Welcome to Personal Web Tutor. Today's problem is right here. It says a ball is rolling horizontally on a frictionless surface at a constant velocity of 2 meters per second. The ball then comes to a 40-degree decline. After the ball goes down the decline, when will it be at 23 meters per second? Also, how far down the decline will the ball have traveled at that time? So the first thing to do here is to draw a picture. We've got this horizontal surface, and then all of a sudden there's a drop. And here's the ball right now. It's rolling, and it's going in that direction. Now when the ball gets right here, the initial velocity is going to be equal to 2 meters per second. It's also going to have gravity, which is our acceleration, is going to be equal to 9.8 meters per second squared. And the question is asking, when will the final velocity equal 23 meters per second? So the formula that comes to mind is the final velocity, which we want to be 23 meters per second, is equal to the initial velocity plus the acceleration and the time times the time. That's what we're looking for. So the part that we want to find right now is we want to find this acceleration. And that's probably the main point of this problem here. The acceleration is due to gravity. However, gravity acts straight down in this direction. So here's my G. And the ball, as it comes rolling down in this direction here, the ball is moving in this direction, so it's not the same direction as G. So we want to find the component of gravity that is moving in the same direction as the ball. So the way we do this is we use our vectors. And you recognize we get a 90-degree angle here. And remember, we're told that the decline is at 40 degrees. So that's this right here. This is our theta, and our theta is equal to 40 degrees. Now we want to see this we want to see this right here as one big right triangle. I'll draw it in blue. And this has a 90 degrees right here. So this 90 degrees is the same as that 90 degrees because we have similar triangles. These two triangles are similar. And so that means that this theta is equal to this theta. Just like if we were to continue and we were to draw those components, this theta right here. So these are alternate interior angles and these are similar angles. So what this means in our equation here is our A is equal to G, but it's only equal to a component of the G of this theta right here. It's this part. So this is opposite the theta, and from what I remember, the sine is equal to opposite over hypotenuse. And so in this case, opposite is this acceleration we're looking for, and the hypotenuse is our G. So that gives me the sine of theta is equal to opposite, which is, we'll call this A parallel. That's the acceleration parallel, divided by G. Or what we get is we get A parallel is equal to G sine theta. And that's what we want to put over here. A parallel g sine of theta. So let's substitute this into our equation. Our equation was V final is equal to V initial plus AT. Our V final, we want to get to 23 meters per second. So we'll put that in there. 23 meters per second. Our initial velocity was 2 meters per second. And we're going to add, instead of A, it's the component of the G, we're going to use this right here. It's going to be G sine theta and then times T. So let's go through here and complete our equation. I'm going to subtract this 2 meters per second over here. So I'm left with 21 meters per second is equal to 9.8 meters per second squared times the sine of 40 degrees. Here, let's just 40 degrees times time. Now the sine of 40 degrees is equal to approximately 0.643. And what I'm going to do is I'm going to divide this side over here. So when I divide, I'm going to multiply by the reciprocal. So here we go. 21 meters per second. This is going to be 1 over 9.8 meters per second squared times 0.643 is equal to T. So notice we've got 1 meter cancels here and a second there and one of those seconds. And after you do all of these calculations, you take 21, divide it by 0.98, and then divide that by 0.643. We get that time is equal to 3.33 seconds. And that's the answer to the first part. The next part of the problem says, hey, how far down did it go during that time? So in order to get that, we're going to go back down here, and the formula we're going to use is V final squared equals V initial squared plus 2 times the acceleration times that distance. Alright, so V final squared equals V initial squared plus 2, and remember the acceleration was G sine of theta, and that's going to be times x. So let's substitute in our values. Our final velocity was 23 meters per second, and we're going to square that. That's equal to 2 meters per second, and we're going to square that, plus 2 times 9.8 meters per second squared times the sine of 40 degrees times x. So we're going to go through and work these out. We get 529 meters squared over second squared equals 4 meters squared over second squared plus, let's see, 19.8, we get 19.6 meters per second squared times the sine of 40 degrees times x. So I'm going to subtract the 4 meters squared over second squared, and that'll give us 525 meters squared over second squared equal to 19.6 meters squared sine 40 degrees times x. Next, I'm going to divide all of this over here. So that leaves me with 525 meters squared second squared times second squared over 19.6 meters times the sine of 40 degrees is equal to x. And notice we got second squares cancel, one of the meters over here cancels. And when I evaluate this whole expression here, I get that x is equal to 41.67 meters. And that is your answer. So what we did was we found the time that it took for it to get to that 23 meters per second. That was right here. It took 33 seconds. And then we solved, and this is how far the ball had to go down in order to get to that. So if you have any questions in regards to this problem or anything else, you can always go to personalwebtutor.com. Here is our website. And you see here we got this little link. It says ask a question. You can go ahead and click on that question. And it comes to a form here. And right here you'll be able to put your question. And you never know, maybe your question will be my next video. Thank you.